So we're going to now prove the Cauchy Riemann conditions. First, we want to show that they're necessary conditions in order that the function is analytic. So remember, it's analytic if the derivative exists and is unique. So remember, the derivative f dashed is given by limit as delta z goes to 0 of f of z plus delta z, I should say, at z naught. Delta z. Now we're going to write we're going to write this bit here, this top bit, as delta u plus I delta v. Okay, no reason why we can't do that. Now, the whole idea is that delta z tends to 0, as delta z tends to 0, it can do so in any direction. So if we choose that delta z is in the x direction, then we can write delta z as delta x. And then we have to have the f dashed of z naught we just replace the delta z by delta x and then take the limit as delta z tends to 0. So if we do that, we simply get delta z is now delta x. We get delta u divided by delta x as delta x tends to 0. So that's just the partial derivative of u with respect to x. And similarly, we get dv by dx as well. So that's one expression for the derivative. But equally, we could also get the derivative if delta z, instead of being delta x, if we make delta z, which we should get the same answer if we make it in the imaginary direction, and then delta z is I times delta y. Then what will we get? Well, we get f. Now we replace delta z by I delta y. So that's going to give us 1 over I times du by dy plus, and then this I is going to cancel with the i's with I below, I over delta v divided by I over delta y, so we just get dv by dy. Now, we need, if the function is analytic, these two things have to be equal. The derivative is independent of how we choose our delta z. So that if they're equal, then the real parts are equal. So we can see that that implies that this equals this, which is this condition here, and that this is equal to this. Well, we can multiply top and bottom by I, and we'll get minus I here and I here. So that's where the minus sign comes from. So what we're trying to prove is that the Cauchy Riemann equations are equivalent to saying that the function is analytic. So we also need to prove the reverse. We need to prove that the Cauchy Riemann conditions themselves imply that the derivative exists. Okay, so we can use Taylor's theorem for multivariable functions to write delta u in this way. So Taylor's theorem says that u of x plus delta x plus u of x plus delta x y plus delta y is equal to u of x y plus sorry, is equal to u of x y plus the differential of u with respect to x times delta x plus the differential of y with respect to difference of u with respect to y times delta y plus HOT, higher order terms, so terms involving delta x squared or delta y squared or delta x times delta y. And we can do exactly the same thing for delta v. What we want in the end is f dashed. We want to see if we can get f dashed from all of this. So we want delta u plus I delta v. Okay, so I'm just to save space, I'm writing du by dx as u sub x and so on. Okay, so if you work out what this delta u plus I delta v is, just substitute all of this in. We collect the delta x terms and collect the delta y terms. Now what I want in the end is everything. I just want everything in terms of derivatives of x. So I'm going to use the Cauchy Riemann conditions to convert du by dy into minus dv by dx. So I'm going to change that into minus dv by dx. And I'm going to change the v dv by dy into du by dx. Okay, so then what I can do is this then is just equal to du by dx plus I vx times delta x. Okay, so this bit here just stays the same. But the reason for doing all of this is that when I multiply this by I delta y, I should get this. Okay, so just check that. So I delta y times u of x is what I've got here, and I delta y times I vx gives me minus vx, which is what I've got here. So plus higher order terms. So this is just my delta z. So in the end, what I have is if I divide both sides by delta z, I've got that in the limit as delta z goes to 0, I have that f dashed, which is this thing here, divided by delta z, is indeed ux plus I vx, which is the derivative that we expect.